Hi, everybody. My name is Andy Ross. I'm a software engineer at Intel, at least for the next 30 hours or so. So you will find there's a personal email address down there, but there'll be another professional one coming soon. Obviously, you can still find me at GitHub at any time. I'm on Discord all the time. I shouldn't be too hard to find. I'm generally wandering around the kernel somewhere, occasionally adding stuff, breaking things as often as not, and generally fixing what I broke at some point in the future. So we're going to talk about linkers, and I'm told that audience participation is always a good thing. So could we get a quick show of hands? Those of you who kind of feel like, linkers are pretty easy, you understand what it works. If you were, put in front of an undergraduate class and asked, does it explain the tool chain and what the linker phase of it does, you could give a good explanation. Like, how many people feel like that level of familiarity with what a linker does? All right, yeah, so pretty decent. I mean, I see lots of waffling back in there, but I think people have a decent idea. Linkers really are pretty easy, all of that. All right, how about another show of hands for people who have actually modified a linker script in Zephyr or elsewhere? All right, a much larger group. All right, and so here we have a disconnect. We have two disjoint sets, the people who need to modify linker scripts and the people who actually feel they understand what linker scripts are. Now, maybe that's because you're sophisticated and understand that there are traps and that sort of thing. We'll be talking about that. Or maybe it's just because linkers are, what we would call in a coarser era, voodoo. Like, a lot of us just don't necessarily understand how they work, and so a lot of us, and myself included, kind of exist in this third group who kind of admit that sure, linkers are easy, but they approach linker scripts with terror. And so that's broadly what this is about. And so we're going to start out, we're going to talk about linkers, going to talk about what Zephyr does that has sort of pushed existing linker technology, which is to say 1970s linker technology, a little past its limits, and a hubristic proposal for ways to address this in the future, which, again, is kind of on brand for me. All right, so what do linkers do, right? It is, again, it's sort of obscure, it's a little weird. Most tool chains, especially on real systems that aren't Zephyr, do a really, really good job of hiding the fact that the linker even exists. But it's not really that complicated, right? I mean, the fundamental problem is compilers work on small bits of code, right? You've got a C file, you've got a single function, you're doing something, you're generating a little bit of code, and it's got to do something. It's got to reference other code. It's got to call another function somewhere, load a variable or whatever. All that stuff exists at addresses. It'll exist at addresses at runtime. CPUs are very good at loading things from addresses if you ignore the fact that, the x86 didn't have IP relative addressing and things like that. So all we need to do is just write a piece of software that sits there and takes these little things and drops them into place and stitches it all up, and we're done. And so fundamentally, that's it. Linkers assign addresses. That's all they're really for. Well, okay, that's all they're supposed to be for. Then you get to the problem of, again, operating system linkage, where we not only want to, stitch things up at runtime, but we also need to take the resulting binary and drop it into some proprietary format, send it to a signing tool, reorganize things such that this thing was here when it was linked and loaded, and then it was loaded at runtime, and it was over here in SRAM, so being written at runtime, that sort of thing. And so Zephyr's got a bunch of tricks that it plays. So we'll start out just with some real quick terminology here. Linking happens in chunks. And now I know that everybody understands linking happens in sections. I'm just going to try to not use that word. It's really pretty complicated. It gets used both for the output section, the .data section, the BSS section, and the input sections. Sections sometimes have unique names in modern usages and historically have not. They don't have unique names at all of that stuff. So we've got chunks. A chunk is just a byte array. It's some generated code. We don't care about what it does necessarily. We're just going to move it around mostly, and then we're going to go in and fix it up a little bit. So they cannot be subdivided. It's, rule number one. This is the smallest unit of anything that is going to be moved around by the linker at runtime. If it's 82 bytes now, it'll be 82 bytes at least, maybe with some padding or whatever, when it ends up in the runtime output. They have names. All of these things have names, and people are familiar with most of them. .ro data, .text, things like that. I don't know why they have a dot in front of them. They always have. Actually, they did in Zephyr for a long time, did not have the dots, and people would complain about it, and now we do, and I still don't know why. They do have these names. It's important to recognize the names are not unique. You know, you can have many .text sections, right? And in fact, if you just call GCC normally and GCC-C, you know, my file.c and my file2.c, you'll get a .text section for, you know, one-to-one for each file that you generate. In practice, we use function sections. We'll talk a little bit about that later. But nonetheless, you know, there's lots of these sections, and they all have names. The names are used as really the only bit of linker script visible metadata, and so Zephyr in particular likes to encode all kinds of crazy information into those names. It is associated with an object file, and that actually almost doesn't matter. We'll get to like the one spot where it does later on, but you know, there's a .o or .obj because we're using CMake file, and it contains a bunch of these chunks, you know, n of these chunks anyway. And each one of them is going to know that it came from this object file. That's not that important, but it will be important later. And then, of course, we have the important stuff. We've got symbols, right? And the symbols are one-to-one with what we think of as C functions, variables, arrays, you know, all of the actual objects that we're going to deal with at runtime. But unlike what you tend to think of as a C function, a C variable, right? Like here's an int, right? It's 4 bytes, right? Well, the symbol's actually just an address. It's a little complicated. The ELF file format does actually have a spot for a size, and the compiler will populate it most of the time, but then you've got jump targets within functions, and those don't have sizes, and so in general, the linker can't trust anything about the size that it's given, so it's just an address. And so you'll notice I've got a little you know, diagram on the side of a typical the typical section. This is the output of a function called myfunc, and GCC has given it a symbol name .text.myfunc, which is the way that F function sections work. It's got a little address table in the middle of some kind of, you know, jump table, or maybe it's an array of global variables, or, you know, something like that it needs to use. And then a little bit farther down, it's got a slightly different looking thing. There's a jump instruction, which has a relocation entry to it. And that's the other big magic behind linkers. And in fact, the only really complicated thing that linkers really do is that the idea of these addresses that it's going to get stitched up is a little bit mutable. I mean, the ones up at the top, the adder relocator, those are just going to be static relocations. Those are just like literally 4-byte or 8-byte addresses of something in memory stored as in, you know, in the native byte order, and it's just the obvious way to do things. The thing in the jump instruction is going to be some kind of, you know, IP relative offset, and it's going to be packed at some number of bits into the instruction, and so the linker needs to understand that it's that kind of relocation and compute the address in maybe a different way. Again, if it's IP relative, it needs to know what the instruction address of the jump is, that sort of thing. These are not complicated. Most of them have a very straightforward expression. In fact, if you just read the ISA reference for whatever architecture you're dealing with, it'll describe exactly how these things work. They are really obscure, though. In fact, almost nothing really documents these things. You would really hope there'd be like some section of the, you know, x86-64 ABI document that dealt with, these are the relocations for the ELF file format for this thing. It's just not there. The only really good reference is the bin-utils source code, which is not the worst thing in the world. But there aren't that many of them, right? I mean, like if you look at actual existing architectures, I mean, I did a lot of, like, you know, you build Zephyr for, you know, this and this and this and this, and then you just, you know, run readelf over the whole thing and just, you know, like find all the unique relocation types. And, you know, there's like, I think 6 variants for x86-64 and only 5 for extensible, which I thought was really nice, although in a classic extensive form, 2 of them weren't even recognized by bin-utils. Like it just shows them as just like number 14 or whatever. The big offender there, and I was a little surprised by this, is ARM64 had, I think, 18 different relocation types. I thought it was a pretty simple ISA. I'm going to need to go and study that a little bit. But nonetheless, this is a small integer number, right? There's not that many kinds of things you need to do, and you only need to do them once, and then they work for everything you're ever going to link. And then finally, there's a little bit more metadata to these chunks, right? I mean, they have some permissions, right? They might be executable. I said RWX here, but it's not that simple, actually. Like ELF obviously has, you know, whether or not they're writable, but also whether or not they're alloc. That's the SHF alloc thing. You would use that for BSS, saying that here's some data, and it's got an address, but I don't actually want to load it at runtime because it's going to be 0-filled, and the operating system is going to handle that for us. They've got an alignment number, like lots and lots of sections generally have, you know, like if they're jump targets, they're going to need to arrive at a particular alignment because the architecture doesn't support jumping to unaligned addresses. Lots of architectures have that kind of rule, that sort of thing. So now that you've got this big set of chunks, right? I mean, you've done all your compiling, you've got a bunch of object files, you've parsed the object files, you pulled in just a bunch of disjoints sets of these chunks, and again, I'm going to try to use that term generically here. You just need to link, and it's really not that hard, right? I mean, this is that bit I told you earlier, like, you know, the actual problem of linking is something I think, you know, lots of people kind of feel they've got a good handle on until you try to edit a linker file and then you're all confused. But the actual problem is straightforward, right? You start out at some, you know, initial set of symbols, right? The, you know, classic ones in our world are boot vectors, interrupt vectors, static definitions of things like system initialization hooks. You know, the sysinit stuff comes in an array. I'm getting ahead of myself there, but there's just, you know, there's a static list of, like, you know, here are the functions or symbols rather that we're going to definitely include, and then after that we're going to go and just traverse the graph and see what references what. You know, again, we've had the graph as defined on the previous slide, and figure out what we need to include. And now that we know what we need to include, we're just going to you could just lay them out. You're just going to go boom, 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 boom. There's a little bit of optimization, right? Like if some of them have very coarse alignment, you don't want to have a 4K thing next to one byte next to another 4K aligned thing, because you're going to have a lot of wasted space. But, you know, that's a straightforward algorithm. Everybody understands that stuff. And that's really all you got to do. The only, like, I get into some complexity here of, like, you know, symbol visibility. Like, you know, as I mentioned earlier, you know, symbols are, you know, not necessarily unique. There are things like, you know, GNU link once sections, which is used typically by C++, like, you know, template instantiations. You have a vector of integers in this file and a vector of integers in this file. They need to be exactly the same code in both cases, and so you have this link once mechanism for doing that. You have comdat, which is a historical anomaly, which is a little unfortunate. That's just the idea that if you say int I, and with no other context, that defines something in BSS, but because of the way that KNRC would treat it, if you do int I in this file and int I in this file, it actually wants those to be the same variable. This is something that trips people up. Like, this is just like one of these weird things about C that you need to be aware of. Anyway, we would need to be aware of it here too, but you know, in all honesty, in a new linker, you can make that a warning condition. We've also got weak symbols. You know, here's the default timer driver that does nothing, but here's the timer driver that works for everybody. We use that trick. We use lots of weak stuff in various driver layers just to make sure that there's always an implementation of something, usually a no-op. Might be kind of, and you notice I'm saying, you know, maybe put some of these rules into the syntax and not the assumptions. Like, maybe we should have a dependency graph that is under programmatic control, but we'll get to that in a bit. And then, you know, having done that, you've got all the chunks laid out. Now you know the addresses of all the things. You just go to each relocation and just assign the address, and that's all you got to do. And you're done. And so you do it with linker scripts. And this is where it starts to go off the rails a little bit. You know, linker scripts are old. The earliest reference I found was in System 3 Unix. I don't know that that was the very first one. The existing linker language did not seem to exist in V7 Unix, so we're talking it arrived somewhere between like 1974 and 1985 on the System 3. You know, somewhere around there, so late 70s, early 80s. You know, it's got some things that look like were good ideas. It's like a declarative language. You sort of specify, here's a section, and here's the stuff I want to go in it, and that sounds like it's a great idea, except of course, for state management and memory size reasons, it is not actually declarative. Like, you hit that thing, here's a section and some stuff to go in, and it goes into the set of all the things and puts those things into it, and then they're not present later on. Likewise, there's an address dot variable you can assign to. People use that for tricks, and that's a sequential thing. It's just going down line by line, so it's not really declarative, but it does look declarative, and that's a useful trick to at least recognize that they started in a good place, right? And the big problem, of course, is that there's no meaningful error reporting, like, at all. Like, I mean, almost any mistake you can make, the linker will happily, silently accept. You can assign the same address twice. It'll just generate whichever one the last one was, you know, same symbol address twice. The 512 megabyte gap is a real bug we've had in Zephyr, where, I mean, I'll talk about the specifics later on, but, you know, yeah, if you have, you know, here's a symbol in a section, and then dot equals, you know, dot plus 500 megabytes, and then another symbol, you're just going to have this enormous blast of zeros between them. Binutils is smart enough to use sparse files, so it's not as bad as it could be. You can a collaborator attempt to find symbol, right, where there's a chunk that has a symbol in it that was expected to be a jump target for something within the chunk, but then because it gets a name later on, like in a provide or something like that, you can end up breaking that. You can just forget stuff, like if you typo a section name or you don't export the right list of exception frames for C++ or whatever. Linker is just happy to just drop that stuff on the ground and forget about it. It doesn't care. And this actually, that by itself is really the reason that Zephyr C++ support has been questionably mature for a very long time, is that every platform ultimately has, it had its own list of linker scripts and section outputs, and nobody really understood the C++ stuff, and so like frame just wasn't included in every platform and that sort of thing. And so it'd be kind of nice if the linker could like at least warn you that, hey, I've got 400 symbols here or 400 chunks here that I was expecting to put somewhere because they're being referenced, and I'm dropping them on the floor instead, so maybe it's a problem. It's a little complicated because they're not really referenced like frame is, and debug information, like the dwarf information actually doesn't have back references from the code. It works in the other direction, so it would need to be a little bit smart about that stuff. You can tell historically it started out with just like one output blob. That was, it would just go linearly through the sections and start here and end here, and great. And here was your PDP-11 data section right there. Later on, the syntax grew, like the ability to have multiple memory sections, memory areas. I don't actually know what the what the technical name is. They're not sections, and that's where if you folks remember the arrow to a memory region syntax, right? That's kind of what that is. In Zephyr, when you build Zephyr, and it gives you the little report at the end saying you've got like 72% of your flash used. That's actually what that's referencing. It's not really. I mean, it is ultimately sourced from device tree or kconfig somewhere, but it's just the linker saying, here, I've got this section, I'm going to spit it out for you. And then later on, you had to use linkers to write ELF files, and ELF being a Unix technology from the late, if anybody knows how System 5 works, they just glued everything together. So ELF has program headers and it has sections, and they are completely disjoint ideas. They're both specified as like offset lengths within the ELF file, but you can have program headers that don't contain any sections, or that contain sections that overlap, or sections that overlap the edge of the program header, or you can have sections that don't go to any program headers. You can have all kinds of crazy stuff. So there's a separate linker section for linker syntax for specifying program headers. And later on, and I think this is a GNU extension, but I actually don't know for sure, you can actually use the linker to separate physical and virtual addresses, so that you can have something that is being linked as if it was going to live at this address at runtime, for example, in SRAM, but is actually being placed at this address over here at linktime, for example, in Flash. And that sounds like it's a great feature, but it actually turns out to be, well, no, that's not on this slide. I'm going to talk about the bugs on that later. We've got a little chunk selection syntax, which is a little bit weird. And everybody who's ever seen this, there's like this wildcard where there's an asterisk specifying all the files in existence, paren, the names of the sections that you want to match, with wildcard syntax, and then some functions or flags that you can apply. In this case, this is sort of a pessimal example where we're using sort by name, and then we use, my sec name, the section name, twice, my sec name dot, by itself, and then dot star. And the reason for that is that GCC, when it generates these things, if you pass f data sections or f function sections or whatever it is, it'll generate a separate section name for each one, but it'll do it by appending a dot. And this is something that wildcard syntax doesn't actually support. You can't write a single wildcard to match them all. So you see this pattern pervasively in Zephyr, and it's a little bit embarrassing. Likewise, keep and sort by name look like nice, functional decomposition kind of things, but there's absolutely no idea of like, the wildcards don't return any data structure over which you can iterate. These are just purely flags that the linker is going to interpret internally. Yeah, I got to the sort thing. The sort only works on the section name, right? You can't do anything else. There's no other metadata. You can't have a table that you source from somewhere else. You can't inspect the data inside the chunks to see what to do. So you'll see actually Zephyr, when it does the system init array, right? There's the list of initialization pointers. We actually encode the priority of each function into the section name of the thing, just because it's the only tool available to us to get these things sorted into the right order at runtime. So let's move on to Zephyr behavior. All right, so that's how linkers work, and that's kind of why linkers are a little annoying, but not as bad as they could be. And I'm like half done already, so I'm going to need to speed up. So, outrageous linker tricks for fun and profit. So the first one here is actually pretty typical. Most people have done something like this with a linker, right, where you've got, multiple C files, and they're all going to define some struct, right, something that you're going to iterate over at runtime. I'm calling it a foo here. And so, here's file 1.c has a myfoo, file 2.c has a myfoo. They're static things, so these are local to those files. They'll be presented to the linker as two different chunks, even though they have the same section name, right? It's important to remember those section names are not unique. And here's a linker script that sits there and creates a foos section, and it'll put a little start marker at the beginning and a start marker at the end, and include with a keep. Got to remember, you got to have the keep, or include the structs between them, and they'll all be sorted. And then or not sorted. I'm not sorting them here. And then at runtime, you can just do code like this in C, where you have you apply those foo start and foo end as if they were actual C objects. I mean, they are sort of. And then just iterate over them with a for loop, and you can initialize them or whatever it is. This isn't too bad. I mean, like Zephyr does this all over the place. We actually have an API to handle this. If you're actually finding yourself writing this code, don't do what I've written here. We have a struct section iterable macro that will do it for you. It's a little boilerplatey because you do need to go into the linker script area where you need to actually declare the fact that you're doing your particular section. But it's cleaner than what I've written here. So this isn't the worst thing in the world. I think this is this is the worst thing. If this is the worst thing we've got, then I think we'll be okay. But we're going to get worse. We also like execute in place, which is, I think, I've always thought this was a little misnamed. I mean, the problem here, of course, is that you've got lots of platforms where you have copious space in ROM, right, like a big flash block or whatever, and limited SRAM, right? So you'd like to keep as much stuff in the flash as possible. You'd like to use the SRAM sparingly, and you've got a bunch of data, just like, int I equals 7, right? That 7 needs to go somewhere, right? That's a data section thing. So it needs to live in the flash, and then you boot up, and then it copies that 7 and all the other .data stuff to the appropriate address in runtime. That's that @ syntax that I was mentioning earlier. Again, this is pretty straightforward, but there are bugs lurking here. One is that, again, the linker script is being at this imperative kind of environment that only looks declarative, has this dot variable. And so you can assign to that dot variable, and lots of linker scripts on various platforms have for things like alignment and that sort of thing. Problem is that dot variable only refers to the normal address, not the @ address. So there's if the two get mixed up, right? You're assigning to dot between two sections that are using that @ they actually will get skewed at runtime. This one is near and dear to my heart because this really was the first really hard Zephyr bug I ever really needed to struggle with. The kind of thing where you're looking at something for 4 days and you just can't figure out why these things are at the wrong address. And it was exactly that. In fact, I was so scarred that I wrote a little Python script to detect that condition, and we carried that in the tree for a long time. But finally, I think we squashed the last of those, and it hasn't reappeared in a long time, so we took it out. This @ syntax stuff is clearly a mistake. This is not the right way. How would you want to do it, right? I mean, I think the way you want to do it, right, is you want the linker, the thing that deals with runtime addresses, to not deal with it at all, right? You've got, here's your ROM being linked with, RO data and text and that sort of thing, and here's your data. Your data is over here, and it's in RAM, and it's got its data, and this is the first byte, and it's got this value, and this is the second byte, and you want to do both. You want to do both of those tasks, and you just want to pull out this data, right, as data, right, as just like an array of bytes, and stick it back into the ROM at the end as another symbol, whatever. Let it do its thing, as like just regular data, as another symbol that you're going to include. Wouldn't it be nice if we could do that? You absolutely can't do that as a regular linker script. Or you kind of can if you give up on the idea of just linking once. You can link as many times as you want. You can link it once to get things partially correct, and then another time to kind of fix things up once you know what's going to be included, mostly, right? And so Zephyr does this repeatedly. And we do it for lots of reasons, right? I mean, there's lots of sort of little intermediate data that depends on knowing what was going to be included in the link to begin with, right? So the ISR tables are a good example. We have a software ISR table, which is a big static array of vector 1, vector 0, vector 1, vector 2, vector 3. And most of those are pointing to a spurious IRQ handler. But this one got registered by a IRQ connect somewhere, and so we're going to stuff its address right in here, and this one was stuffed in there. You don't know which ones of those actually need to be stuffed until you look at the list of referenced things and see, this driver was built, and therefore its ISR is in place. So we link once, and then we link again to get the ISR table right. Likewise, when you're using user space, there's a list of kernel objects. They all have a gperf generated hash generator, so you can work backward to the address of work backwards to the array index of the kernel object from its address, so that we don't, need to sit there and, traverse runtime data and all of that sort of thing. It's a great trick. It iterates over the dwarf debug information in the output data. But again, it requires that everything be generated once so that you know which kernel objects are there. Threads have indexes when you're using user space, and that's because there's a permissions bit array for each thread that we have. And this is the nice thing about being a tiny little RTOS is we can do this sort of thing with permissions of just a bit mask, because we're not going to have more than 64 threads, right? And that list of threads is, again, a static thing. Static threads need to link once to figure out which ones are actually going to be included. There's a DTS device handle data structure, which is like a slightly smaller than pointer representation of the... Oh, I'm sorry, we've got a question? 5 minutes, all right. Yeah, we're going to go real fast. Well, we got a break at the end, so I'll go fast. So let's go on to the next one. The next one is static libraries. Zephyr uses these all over the place, and it's actually kind of a mistake. If you think about it, like a static library doesn't make any sense when you're linking the entire project all at once. That's what Zephyr does. We don't ship these static libraries. And so the question is, why do we do them? And one answer is, and it's actually on the right-hand side, is we do it just by cargo cult. Like that seems to be the way subsystems work. So I'm going to make a library. C makes it nice and easy. It seems tidy. It's sort of a mistake, right? It's clearly wasted work. But the real reason we do it, and this is actually used at least once in the kernel and probably in a couple of other places too, is it's actually this kind of terrible hack for dependency management. And this is where that file comes in on your chunk references. The chunks know what file they were in, and there's this rule that in a static library, if any chunk within a file gets referenced, the entire file, every chunk in the file, gets pulled out and presented to the link. And so that's a way to say, here's an API or a subsystem, and if anything is using that subsystem, then please, pull the whole thing out and include the drivers, and then you'll get the ISR and the, static initializers and all of that stuff that you would otherwise get. And it sounds like a great idea. The problem is, one is it's ad hoc and kind of confusing, because if you're using the API but only a macro or an inline function or whatever, the linker never sees it and you don't get that behavior. The other one is it's just a total layering violation. This is what kconfig is for, right? I mean, you should be using kconfig if you've got some conditionally compiled thing. So wouldn't it be nice if the linker had some tools to do this, like predicate this symbol on this kconfig, allow it to be built, you build your ISR every time if the subsystem is enabled or whatever, but just make sure that it's actually used, or include it only if this other subsystem is used, right? That's essentially like a reverse dependency. Instead of saying this depends on the other thing, it's like, this should actually depend on me, right? And now we go really off the rails, and this I actually discussed last year, so I don't know that I necessarily need to do it again. The Intel Audio DSP is an Extensa device. Extensa has a cache incoherent architecture, which is a terrible problem for an operating system. And the solution is we just need to make sure we segregate, which data is allowed to be cached. Your thread stacks can be cached. Data that is going to be safe is allowed to be cached. And almost everything else is uncached by default, and so you need to figure that out. And this is made to work because the hardware actually maps RAM twice, and Extensa has a cache attribute bit so that you can set it differently, and they're set in these 512 megabytes chunks. This is what I was mentioning earlier. And we made this work with the linker, and we did it by assigning to dot, right? So I'm linking my dot text. Well, that's text, that's cached. Okay, great, I want that to be cached. Now I'm going to shift over to RO data, which needs to live next to text because it's not mutable. But that one, okay, no, but that can be cached too because that's read only. And now I go to the data. Dot data is going to be mutable. That is not cached, so you assign to this. You just bounced 512 megabytes this way, 512 megabytes this way, back and forth. It does work, and in some sense, I'm kind of proud of it. It's really complicated. It's especially really complicated with our linking situation where so much of this stuff is based on the C preprocessor. We're including linker files. It's very hard to remember which context you're in based on the context where you're writing your code. And then at the end, of course, you end up with this very disjoint object file, and you need to use a ton of object copies, just object copy to this, object copy to this, to reassign all of the symbol addresses. And that's managed with a Python script, which is essentially another linker pass, right? So it's kind of a mess. The syntax doesn't actually look like this at runtime. We've got a fairly complicated preprocessor API to abstract out some of the worst of it, but it's that level of hackery. And then there's a bunch of other examples too, which clearly I'm not going to get to. So I'm going to zoom past this slide, and folks can kind of take a look. Some of these are kind of interesting. I will do like auxiliary memory spaces are an important one, where like a lot of architectures boot from like one area of RAM, and then do the BSS clear or a copy of the .text to another area, like initializing SRAM or whatever. That gets managed by the linker so that you can have references in one direction and not the other. And again, that ends up kind of difficult and error prone. So what are we going to do? We're going to write our own linker, right? Again, total hubris, but on brand as far as I go, as far as I'm concerned. So reasons not to, right? I mean, it's big and complicated. It's really not. I mean, again, they made this work on a PDP-11, and the problem has not changed, right? It's slow. Yeah, well, tell me about it. First, linking is not a significant part of the Zephyr build. Also, we do it 3 times. If we really cared about performance, we would have fixed that, well in the past. And it's the toolchains job, and I think that's a much more reasonable argument, right? I mean, it's like, realistically, are we ever going to replace bin utils? No, we aren't. But I think the contention is that Zephyr is far enough down the road of again, pushing these tools past where they were intended, that I think, in fact, owning our little area of the tool chain is probably a good idea. And again, I mean, if it's a better linker, it's a better linker, and I think there's argument that you might want to push this stuff backwards. And what might it look like? All right, well, first thing is, of course, likely to be in Python. Certainly the extension needs to be some kind of straightforward programming language lots of people will deal with. Remember, our disjoint set of people who understand linking versus people who have to do it was a problem. So yeah, if you need people to do it, let's pick a representation that people are going to all be understand with. Like, lots and lots of people can deal with a straightforward Python API. This would be a straightforward Python API. I think most people recognize that would be useful. The linker scripts then become subsystem-based modules, that sort of thing. You can split that dependency step from relocate. Remember, almost all of the linker trickery we do has nothing to do, in fact, almost all the linker trickery we do has nothing to do with the byte content of the output. It's all about the dependency management. It's all about looking at that graph of what are we going to include, and then creating some new stuff, modifying some existing stuff, doing something else, and then doing that dependency graph again, and then continuing on. If we could actually represent those 2 passes as a distinct phase, you can do all your linking in just one pass. I mean, obviously, there's still some iteration that would need to happen, but you wouldn't need to constantly be reparsing the same files. And so this was going to be a giant selection of slides, and I squished it all down. But this is Pseudo Code. This is not an actual prototype. I was hoping to have one for you. I don't really have one for you yet. But this is the kind of complexity that we're actually looking at. I mean, these things are, you can read the Python comments, and in fact, go grab the PDF yourself and take a look. But most of the problems we discussed earlier kind of boil down to, like 6-7 lines of code. I mean, in reality, you would want a bunch of error handling and warning checkery and all of that stuff. But the actual like Zephyr logic, the things that are specific to the problems we have, becomes really pretty straightforward and really pretty trivial. And I think you'll be amused by some of the typos that got left in these screenshots too. But I'm going to blast past that because I do want to get to the last thing. So obviously advantages. Error checking is the big one, right? The list of these voodoo mistakes that you can make with a linker script can be squished way, way down. I mean, sure, you can look for, undefined and duplicate symbols, that existing linkers do that, but also, what if you've got a bunch of weak definitions? What if you've got GNU link once definitions that don't match, right? Like, that's a classic C++ bug, is right, you've got a stale build, and here's a .o file with a template instantiation of this thing, and here's a .o file with a template instantiation of a modified version of a struct, and they don't match. Comdat, I mentioned this earlier, would be kind of nice if that was a warning condition. Almost never is that what people actually want. Comdat, by the way, is a Microsoft term. There's no other, like, I couldn't find any other name for this rule. Things like orphan symbols, I mentioned that earlier, just forgetting drivers, forgetting that, like there's a driver and subsystem that got built, but there was no DTS instantiation that told it to actually make a struct device. That's clearly a warning condition, right? I mean, clearly you shouldn't be building that driver. You probably made a mistake, right? We can totally do that. The all zero static initializer thing, which is an optimization that the existing linker does, or the existing compiler does, right? If you have a int I bracket equals curly 0 0 0 0 0 curly. That's an array of zeros. The compiler will sit there and say, okay, you've initialized it to 0. I'm going to put that in BSS. And that actually is a problem with our multi-stage link. We had a bug just like a month and a half ago that actually Daniel Lung fixed this one. I didn't. I don't get the glory for that one. But it actually turned out to be exactly that. It was the link put it into BSS, and because it was in BSS, it got dropped because it was in a special section, right? We just didn't have it there, and so the list of thread IDs just wasn't generated, or wasn't generated at the right size because there was some alignment padding or whatever, and so things basically blew up on x86 when I added a thread to a completely unrelated test. Future-proof validation. I mean, obviously, just the rules that I mentioned earlier about no calling from your initialization region into the region to be initialized. You can enforce that with a linker. It would be kind of nice. And maybe it might even be faster. I mean, again, Python's not a fast environment, but the actual problems we're dealing with are straightforward, and if you can do it all in a linear pass on the data, that's mostly I/O bound. And then the actual CPU bound stuff, again, just going and writing all of those relocations, is one, incredibly parallelizable, but also something that's almost generatable as binary code from Python. I mean, there are LLVM implementations where you can generate some quick code. We could almost write some assembly in x86 and ARM and things like that would actually do the relocations. If you only got a few dozen of them, it's not a big deal. And again, we do it 3 times, so we don't really need to be that much. I mean, we can be 3 times slower right out of the gate. So I think we're pretty good. There's a compatibility problem of, how does this actually work? Like, imagine like I've got it ready and it's all set. Obviously we just can't throw bin utils out. Everybody's going to flip out. Most platforms, again, have existing linker files that have a bunch of platform dependence hackery that's already there. That would all need to be duplicated into 2 different versions. Some projects might actually require specific tooling. In fact, Chris Freet is finishing up his talk right over there talking about native POSIX on macOS, which is Mako binaries, different binary format, not ELF. You can't use the existing linker scripts because it doesn't support them. And so he's dealing with a lot of exactly these problems. So the first solution, obviously, is just maintain both schemes for a couple of releases, right? It's expensive long term. Like every time you add a feature, you need to add it to both. That's not what we really want. That's clearly where we would start. Solution number 2 is just, throw bin utils out as soon as we can. I would love that. Yeah, I guarantee that will never work. Somebody's going to be stuck with bin utils. And so how about we have, this, again, we've done almost all the work. We've done all the linking and relocating, and we've got a blob that we can stick anywhere. And how about we leave the relocations in place and emit the blob as another object file? We could generate a stub linker script, right? Like, here is your object file, which is kind of like a library. There was a question actually in Discord about, Zephyr as a static library. That's kind of like what this is. And a really tiny, an 8-9 line linker script that would generate it, and then use that as a stub for, some other layer of integration that you can then add your platform dependencies, add your HAL libraries, add all of that stuff, and then use bin utils as a linker for that. I think that's actually pretty reasonable. And it has the advantage that it works with LTO, or it probably works with LTO. And I am no expert on the broad world of link time optimization, but it's great, it's new, it's fun, it's something that big projects have started to embrace. I mean, again, like Chromium and Firefox are really into this stuff. Linux distros are lagging a little bit. So there's not a lot of really serious integration that's been done yet, but it does work and it is there. And it does a lot of what we're actually trying to do right now in Zephyr with a lot of trickery, right? I mean, we've got a lot of header files that define inline functions that turn into macros that'll do this or that, all trying to hyper optimize stuff at runtime. And it does it for free, and it does it great by looking at saying, okay, this is this, and it's always a constant, and this is always a constant. I can fold those together, and this call here is always a leaf, and so I can eliminate that and inline it and all of that stuff, even if they're not visible to the same C code. And so I think it's a great idea. The basic idea is, pretty straightforward, right? Instead of the chunks containing binary code, they just contain source code, basically. They contain a syntax tree, a parse tree of whatever the compiler saw at compile time. And the linker doesn't do anything but check the dependency tree. It's exactly the same problem, right? It's going to go through, it's going to figure out what needs to be included, and it's going to grab all that code and then give it back to the compiler to say, here's a blob of code, please link this into a single chunk for me. It's almost exactly the same problem with that preprocessor problem we were just talking about. It's a little complicated by the fact that the tools themselves are a little divergent. LLVM actually has an API exactly like that, where you can say, here's a bunch of these chunks, and please take them and then give me back a single relocatable chunk of binary code that I can then use. GCC actually wants to call the linker back itself. It's not really a toolkit kind of environment. So GCC would actually need to take our relocatable chunk and then do that. But again, that's exactly what we've got. We can totally do that. We've solved the problem that LTO actually needs to have solved, which I think is actually kind of cool. And so, I mean, I think, this isn't necessarily a V1 version, but I think there's real hope that the LTO kind of follows on this as a very straightforward extension. And I think realistically, I think that becomes the big value add here. I mean, I think if we get through this entire thing and I've got a brand new linker and nothing else as far as new features, I think it's kind of a failure. If it's got LTO, I think it's going to be sort of hit out of the park kind of success. So I think this is really where we come down to. And I actually got through most of this already, so I think I'm just going to. Yeah, all right, I'm going to call it end right here if anybody has any questions, all right? All right, yeah, and I went over by 10 minutes already, so we're out of time. If not, yeah, come watch this space and come heckle me in the coming month or two, and we'll see what we can make happen. I'm reasonably hopeful. Yeah. Yeah, well, I mean, to some extent, this is still dependent on me having a prototype. The hope was I would have a prototype here, but I don't because, life intervenes and I'm moving jobs and all that. But yes, no, absolutely reach out. Find me on GitHub. Find me on Discord if you're interested in this. Especially folks who have had to manage some of the crazier linker environments, I think would be really nice to have input. So, yes. Okay, I swear I did not pay anybody. All right, yeah, it's very much a labor of pain. Yes. So LLVM doesn't do linkage per se. It does what I guess you would call in the language that I've introduced here, it does chunk generation. So and it's a little complicated because it interacts with the language runtimes too. So like if you're linking Rust, what you don't tend to get is just a bunch of object files that you're expected to link. The compiler will just give you the blob all by itself, kind of like what I was talking about. Like here's your single relocatable chunk. That's kind of the Rust model. Clang is much closer to this model right here. And in fact, they're rolling out their new LLD linker. Uses exactly the same syntax. It's mostly GCC or rather binutils compatible. So it doesn't really solve that problem. And this is fairly. I mean, the complaints about linkers are not new. Obviously binutils actually has two, right? There's the classic binutils LD, and there's also one called Gold, which is it was written about like 15 years ago. It's not even really new software, but written with a clear eye toward performance. When linking giant projects, like Linux or Chromium or especially Chromium, or like big C++ projects where there's really a lot of linker symbols floating around. C++ has this terrible problem of like generating everything 1,000 times. Like, again, vector of int appears in like, every object file, and then something's got to go through all of those and unify them and throw out the ones that don't belong. So yeah. So the simple answer being, LLVM doesn't provide any tools. The LLD linker doesn't solve any of the problems Zephyr has. So, it would be, it's one of those situations where I hesitate to say that, clearly we must write our own. No one has solved our problems, because I think a lot of people have dealt with exactly this kind of problem before. I will say, and I think I'm old enough to get away with this now, I think Zephyr is, like, we're beyond the cutting edge. I mean, I think what we're doing with the System 5 linkage paradigm is well beyond what basically anybody has managed to deal with ever. I mean, if you look at all the different platforms that we've got on a single OS base, mostly with a single linker script. I mean, again, there's a lot of platform hackery that's going on, but for the most part, like all of these optimizations that I was talking about, like arrays of ISRs and all of that, that's all generic code, and we're making it work on every single platform with significant pain. That's the problem. Right. Yeah. Exactly. And that's exactly the kind of problem that we deal with. And I alluded to that a little bit with the multiple memory spaces. That the audio DSP, for example, comes up running in what's called IMR memory, which is actually just it's a sequestered piece of system DRAM, which is incredibly slow. Like it's like 80 cycles per access or something like that. And so the job of the little bootloader is to take the stuff that got copied into this large region of IMR and then copy it to the SRAM. And the SRAM needs to be initialized and powered on, and there's a clocking generator you need to get right and all of that stuff. So there's some complicated initialization before getting that done. But then the suspend states, and we don't have this working yet, so I don't want to be like proclaim too much, but the suspend states would really like to be able to power that SRAM off. It comes in 64K banks, and there depends on the version of the chip, but we've got multiple ones of them, so it'd be really nice to be able to turn this one off and leave these guys on or whatever.
I think that problem is also a syntax problem inside Zephyr. Like how do you say that this data variable is important and retained,
Yep.
whereas this one is reinitializing?
Right. And the answer is we do it with linker sections. There's a underscore IMR, macro, basically. It just expands to a GCC attribute that puts it in a special section, and the linker script knows that IMR memory needs to go in the special place. And like I say, it's a terrible hack, because right now there's nothing that's going to prevent you from sitting there in the boot code, which is an IMR, and then calling out to memcopy or some standard library thing that just isn't, it's not an SRAM yet. So it'd be really nice to have a set of tools to build that kind of thing. Exactly the form it would take, I don't know, but I know what I would want the tool set to look like, and it would look like, a bunch of Python scripts. And I say this, again, talking about brand management earlier, right? There's nothing that I'm known for within Zephyr. It is a facility with an expertise and evangelism of the Python language, right? Yeah, I can feel Marty about to kill me right now, but I'm not. Yeah, I'm not necessarily the best person to sit there and evangelize Python as the representation. But I think something like that is, I think, clearly the right choice. So cool. All right.